What on earth is this? And what in heaven's name is this? The answer is that these are examples of entity relationship diagrams, or ERDs. But what exactly is an ERD? An ERD is a way of expressing the logical design of a database in a visual way. In this video, we're going to explore how an ERD helps to clarify crucial aspects of what's going on in a database design. We're going to look at a couple of types of notation you can use in ERDs, Chen notation and crow's foot notation. By the end of the video, you'll understand how ERDs convey information, how they help in database design, and how you can make useful ERDs of your own. This is Decomplexify, bringing a welcome dose of simplicity to complex topics. Suppose we want to design a database for people in our local community, a database that keeps track of which people own which pets. We would like the database to capture the names of the owners, the names of the pets, photos of the pets, the addresses where the pets live, and what type of animal each pet is. This would be dog, cat, hamster, or whatever. These are what we might call the information requirements that our database needs to meet. A useful way to get started on turning requirements into a database design is to identify all the nouns that appear in the requirements statement. Let's circle them. Here are the words we circled. It's helpful if we get all the words into the singular rather than in the plural, so we'll change the word people to person. We can shorten the list by getting rid of redundant words. The first two words on the list are person and owner, but since an owner is a person, we probably don't need both words. We'll retain the word person and discard the word owner. Similarly, given that our list contains the word pet, we can get rid of the word animal because the only animals being talked about here are pets. Finally, to avoid ambiguity, let's clarify what we mean by the very open-ended word type. According to our requirement, type means what type of animal a pet is, a dog or a cat, for example. So, for clarity, let's replace type with pet type. We now have 6 terms: person, pet, name, photo, pet type, and address. Each of these 6 terms designates a particular kind of thing that our database will need to keep track of. The database needs to keep track of people, it needs to keep track of pets, and so on. But that's not all. The database also needs to keep track of the relationships between things. For example, according to our requirement, it's important that a particular pet has a relationship to a particular person. Here are 2 pets, a cat named Cleo and a dog named Buster, and here is a person named Trisha Anderson. Trisha owns Cleo and Buster. The database needs to capture this fact. Let's try and sketch out the kinds of relationships that exist among people, pets, names, photos, pet types, and addresses. A person owns a pet. A person has a name. A pet has a name. A photo depicts a pet. A pet has a pet type. A pet resides at an address. This sketch communicates the kinds of things our database needs to keep track of, and the kinds of relationships those things have to each other. It's a good start, but it's not quite enough. When it comes to relationships, there are some important questions that the sketch doesn't answer. For example, the sketch tells us that pets can be owned by people. This is what the line connecting person to pet is expressing. But what the sketch doesn't tell us is how many people can own a pet. Can a pet have 2 owners? Can it have 3 or 4 or any number of owners? Can it be an orphaned pet, a pet with 0 owners? Really getting to grips with the requirements means asking and answering questions like these, questions about what we call the cardinality of relationships. Cardinality means how many of one thing are associated with how many of another thing. Let's go through the relationships in the sketch and for each one, let's write down what we're deciding the cardinality of the relationship is, along with a justification for making that decision. Decisions about cardinality aren't always clear-cut, but whatever decisions you make need to have plausible reasons behind them. The justifications that appear on the screen alongside each relationship go into a certain amount of detail, so you may want to pause the video to give yourself time to read them. We are going to say that each pet is owned by 0 or more people, and each person owns 0 or more pets. Each person has one name, and each name belongs to 0 or more people. Each pet has one name, and each name belongs to 0 or more pets. Each photo depicts one pet, and each pet is depicted in 0 or more photos. Each pet type applies to 0 or more pets, and each pet has one pet type. Each pet resides at 0 or 1 address, and each address has 0 or more pets living in it. Deciding on the cardinality of each relationship, as we've done here, is a crucial step in the database design process. Get it wrong, and you'll probably end up with a database system that doesn't do what it's supposed to do. For example, if you decide that each name belongs to exactly one pet, then at some point the users of the system are likely to encounter an error message like this. This is what happens when the database doesn't support 2 pets having the same name. Now that we've decided the cardinalities of all the relationships, let's create an entity relationship diagram that includes them. For this exercise, we're going to use a diagramming style known as Chen notation. In Chen notation, each of the nouns we identified gets its own box. Person, pet, photo, we place all of these in boxes, and we refer to them as entities. We represent each relationship by a diamond shape connected up to the relevant entities using lines. The next thing we need to do is express the cardinalities of the relationships. In Chen notation, cardinalities are expressed like this. Reading from the daughter end of the relationship to the mother end of the relationship, we say a daughter has a maximum of 1 mother. Of course, the kind of mother we have in mind in this illustration is a biological mother. Reading from the mother end of the relationship to the daughter end of the relationship, we say a mother has a maximum of n daughters. And because n means any number, this is a way of saying there's no defined limit to how many daughters a mother can have. Chen notation can also provide some information about minimum numbers, the minimum number of mothers a daughter can have, and the minimum number of daughters a mother can have. The minimum number of mothers a daughter can have is 1. The fact that the minimum isn't 0 implies that for daughters, the relationship to a mother is universal. We won't find any examples of a daughter with no biological mother. This universal relationship, which every daughter must participate in, is shown by a double line. The minimum number of daughters a mother may have is 0. This amounts to saying that, for mothers, the relationship to a daughter is not universal. Some mothers don't have any daughters. This sort of non-universal relationship is shown by a single line rather than a double one. Going back to our pet ownership model, let's add in all the cardinalities. Here is what they look like. Notice where the double lines are. A pet must have a name. A person must have a name. A pet must have a pet type. All of these relationships are shown with double lines. Notice the relationship between pet and person. A person owns a maximum of n pets, and a pet is owned by a maximum of m people. Like the letter N, the letter M simply means unlimited, any number. The only reason we don't use the letter N on both sides of the relationship is because we don't want to confuse people into thinking that these two n's stand for two numbers that are literally equal to each other. The diagram now gives a clear idea of what all the relationships are. If we want, We can make the diagram even more informative by adding information about the kinds of attributes each entity has. Attributes meaning characteristics or properties that we want our database to be able to keep track of. For example, we might want to say that each photo has an image file name and a date uploaded. Image file name and date uploaded are attributes of the photo entity. Each one becomes an oval connected to the entity by a line. And we underline image file name to highlight that image file name is unique. We're going to assume here that the system assigns a unique one upon photo upload, and so image file name uniquely identifies a photo. Although in this particular case the unique identifier was just a single attribute, image file name, sometimes the unique identifier will consist of a combination of attributes. When it does, you need to underline each such attribute to communicate this. For example, if we had a geographical location entity, whose unique identifier was the combination of a latitude and a longitude, we would underline both latitude and longitude. A slightly different convention applies when we have an entity whose identity is bound up with the identity of a parent entity. For example, there might be orders and order lines, with each order encompassing multiple lines, line 1, line 2, and so on. The unique identifier for the order entity is order number. The unique identifier for the order line entity is the combination of order number and line sequence number. However, in Chen notation, we don't explicitly show order number as an attribute of order line, even though in a very real sense it is one. Instead, we add a double border to the order line box and a double border to the relationship between order line and order. The double border signifies that order line is a so-called weak entity, meaning an entity which derives part of its identity from a related entity, in this case order. It is therefore understood that line sequence number, the underlined attribute, doesn't identify order line all on its own. Instead, order line is identified by its parent entity's unique identifier, order number, in combination with line sequence number. A set of attributes could be drawn up for every entity in our diagram. We won't actually go through that exercise in this video. We will, however, make a slight amendment to the diagram. This amendment has to do with how names are represented. Each pet has exactly one name, and each person has exactly one name. So why not make name an attribute of the pet entity, and likewise, why not make name an attribute of the person entity? This seems more natural than making name an entity in its own right. Chen notation includes a few other visual conventions that allow you to convey even more information about entities, relationships, and attributes. But let's not get too bogged down in the details of the notation. Many different notations exist for ERDs, with Chen notation just being one of them. Outside of educational settings, a much more popular notation for ERDs, which happens to be my own preferred notation, is crow's foot notation. In crow's foot notation, we don't bother with diamond shapes to represent relationships. Just drawing a line between two entities is enough to signify that there is a relationship between them. What we put at each end of a relationship line expresses the cardinality of the relationship. In this notation, all you have to do to express cardinalities is to draw at the end of each line two symbols, the first expressing a minimum number and the second representing a maximum number. What are the symbols that are available for you to choose from? They are the 0 symbol, the 1 symbol, and the multiple or many symbol. A circle shape, which looks like a 0, means 0. A vertical line, which looks like a 1, means 1. And a crow's foot shape, which has diagonal prongs on either side of the relationship line, means multiple or many. Here, we are being told that each mother has 0 or more daughters. The 0 symbol represents the minimum number of daughters, and the many symbol represents the maximum number of daughters. Looking to the other end of the relationship line, we see that each daughter has a minimum of one mother and a maximum of one mother. Or to express it more simply, exactly one mother. So, for each relationship line that exists in an ERD, we draw in 4 cardinality symbols, 2 at one end and 2 at the other end. At a given end, the first symbol represents a minimum number and the second symbol represents a maximum number. When trying to express relationships in an ERD, you should focus most of your thinking on the maximum numbers. The maximum numbers are crucial to defining the basic nature of a relationship. If we put aside the minimum numbers for the moment and focus only on the maximum numbers, it becomes apparent that there are 3 basic kinds of relationships. The first kind has the crow's foot symbol at both ends. Each pet can be owned by multiple people, and each person can own multiple pets. We call this a many-to-many relationship. The second kind has the crow's foot symbol at just one end, as in our mother-daughter example. We call this a one-to-many relationship, or equivalently, if we're reading it in the other direction, a many-to-one relationship. The third kind of relationship has a 1 at both ends, and no crow's feet symbols. Each employee has one employee ID card, and each employee ID card belongs to one employee. We call this a one-to-one relationship. In crow's foot notation, the entity relationship diagram for our people and pets database would look like this. We can see, as before, that each pet is owned by 0 or more people, and each person owns 0 or more pets. So the relationship between pet and person is many-to-many. Each photo depicts one pet, and each pet is depicted in 0 or more photos. So the relationship between pet and photo is one-to-many. Each pet type applies to 0 or more pets, and each pet has one pet type. So the relationship between pet type and pet is one-to-many. Each pet resides at 0 or 1 address, and each address has 0 or more pets living in it. So the relationship between address and pet is one-to-many. And we can make the diagram even more informative by adding attributes. Our goal here isn't necessarily to show every attribute that's going to be in the finished database, but we should at least show uniquely identifying attributes. That is, attributes that serve to uniquely identify an entity, along with perhaps a handful of other significant attributes of the entity. Notice that some attributes have an indicator beside them saying PK, which means that the attribute is a primary key attribute. Others have an indicator beside them saying FK, which means that the attribute is a foreign key attribute. In other words, an attribute which can also be found elsewhere as a primary key attribute on another entity. The diagram has now reached a stage where we can translate it into the skeleton of a relational database design, with tables, columns, constraints, and so on. For each entity on the diagram, we can create a table. For each attribute of an entity, we can create a column within the table, along with whatever other columns we think are needed. We can define primary and foreign keys for each table, in line with the primary and foreign keys shown on each entity in the diagram. Each one-to-many or one-to-one relationship in the diagram will become a foreign key constraint in the database. The only kind of relationship we can't express using a foreign key constraint is a many-to-many relationship, like the relationship between person and pet. But there is a way around this. Whenever we encounter a many-to-many relationship between two entities, we can think of it as two one-to-many relationships. Here we have introduced a new entity called pet ownership in between our existing entities person and pet. If Jenny and Bill both own Rover, then Jenny's ownership of Rover is one instance of pet ownership, and Bill's ownership of Rover is another instance of pet ownership. If Martin owns Skipper and Claude, then Martin's ownership of Skipper is one instance of pet ownership, and Martin's ownership of Claude is another instance of pet ownership. The relationship between person and pet ownership is one-to-many. The relationship between pet and pet ownership is one-to-many. The new entity, pet ownership, becomes a table in the database, and both relationships to it can be captured as ordinary foreign key constraints. This completes our discussion of entity relationship diagrams. I hope you found it helpful. If you have any comments or questions on what you've just heard, please go ahead and post them in the comments section below. And if you have any suggestions for other complex topics that you'd like to see explained on Decomplexify, let me know in the comments. Feel free to like, share, and subscribe. So long, and thanks for watching.